Okay, so we have come back to number theory once again, and so let's continue. Here in this one, we are given two non-zero integers a and b, and for them we have to establish these things. So there are three parts. In the first one, we have to prove that the GCD of a and b will be equal to their LCM if and only if a is plus or minus b, that is either a and b are equal or their sum is 0. And in the second one, we have a property which looks like another one that we already have seen for GCD. In fact, that's a result, that's a theorem, that if you multiply two integers a and b, I mean our a and b in this case of course, by a positive integer k, then the LCM of ka and kb is k times the LCM of a and b. The similar one for GCD is of course the one where you have GCD in place of LCM, and there of course a and b both need not be non-zero, only one needs to be non-zero. I mean at least one needs to be non-zero, but this one is just like that GCD property. And in this third one, m is given to be any common multiple of a and b. That means m is an integer that is divisible by both a and b. Then we have to prove that the LCM of a and b divides m. If you recall the actual definition of LCM, LCM is a positive integer which is a common multiple of a and b, and it's the smallest such positive integer which is a common multiple of a and b. Here, however, we have to prove that the LCM divides any common multiple, not necessarily positive. This m can be negative also, and hint is also given. So we will follow this hint. So let's now start the solution. So in the first one we have this GCD is LCM if and only if a is plus or minus b. That means there are two implications to be proved, one of which will be easier than the other. That's almost always the case with this type of statements which are double implications. One side is usually much easier to prove. So let's handle the easy one first. Let a be plus b or minus b. Then it's quite easy to prove that the GCD of a and b is this, which is also equal to the LCM. Now the small arguments that are needed to have this from this, I am not showing them here. Okay, so I leave that to you to figure out, and if you don't get it at all, then of course you tell me in the comment section, we can discuss. So this part I am just simply leaving. Note one more thing, that we have taken the absolute value of a and not a itself. That's because we are only given that a and b are both non-zero. A may be negative also, but by definition both GCD and LCM are positive integers. So that's why we have to take absolute value. Now we we show the converse. Conversely, let the GCD of a and b be equal to the LCM of a and b. Then okay, now LCM by definition is a common multiple of a and b. That means it is an integer, it's a positive integer that is divisible by both a and b. Now since it's divisible by a, So it is also divisible by the absolute value of A naturally, because the absolute value of A is either A or minus A. So that's why we write the absolute value of A divides the LCM of A and B, which by our hypothesis is actually also the GCD of A and B. Okay, this is something we are getting. That means ultimately we are getting the relation that the absolute value of A divides GCD of A and B. But at the same time, and this next thing will come directly from the definition of GCD. GCD of A and B, on the other hand, is a positive common divisor of A and B. That means it is something that divides both A and B. Now, since it divides A, it will also divide the absolute value of A also. So, following that argument, we get this. If you really want to write in detail, you have to write by definition, also by definition GCD of A and B divides A, but A also divides absolute value of A, and divisibility, since the relation of one thing being divisible by other is transitive, so you get this. But we of course don't write that much, that we understand. Now, since this and GCD of A and B are both positive, we have what? What do we normally have when we have two relations like this? Like this is dividing this and the other thing also, that is, this is dividing this. The normal conclusion that we have from two such divisibility relations is that one of them is either equal to the other or the minus of that. However, the numbers we are dealing with here are both positive, and that is why they must be equal. One of them cannot be the negative of the other due to positivity. And they of course are both positive. That's because GCD is positive by definition, and this is positive because A is non-zero integer. We have this. So under the hypothesis that GCD and LCM are equal, we have shown that thing. One can similarly show that this is also equal to the absolute value of B. So whatever we did, starting from here, we clearly concentrated on A, but there is no distinction between A and B. One is not preferred to the other in this situation. In other words, in the given situation, A and B are symmetric. So that's why whatever we did with A, we can do an exactly similar thing with B, and we will get a similar conclusion, that is this thing. Thus, these two are equal, and which of course implies what we want. Which implies that A is plus or minus B. So that is part A. Next, in part B, we have to prove that if k is a positive integer, then LCM of ka and kb is k times the LCM of a and b. Okay, and here we, in fact, we will just see a sequence of equalities, and that itself will give us the result. And along the way, of course, we have to use one of the results that we have already seen in the text. When we use it, we will recognize what we are using. So I am not going to write anything extra. I just simply write we have LCM will not have enough space here. LCM of Ka and Kb. Now in place of Ka and Kb, I am going to write absolute value of Ka and absolute value of Kb. Now note that even before you take this step, there is one thing that should be considered, just for the sake of seeing that everything is in order and in fact everything makes sense. A and B are given to be non-zero integers and k is a given positive integer. So Ka and Kb are also both non-zero, and that's why their LCM exists in the first place. So that is okay. Now what have we done here? This we discussed before also. Namely, when you find GCD or LCM, the numbers that are involved, their signs do not matter. In other words, if say you are having two non-zero integers p and q, then LCM of p, because LCM by definition is itself a positive integer satisfying some conditions, so LCM of p and q is equal to LCM of minus p and q, which is equal to LCM of p and minus q, and that is equal to the LCM of minus p and minus q. So it does not matter what signs they have. So in general, we can just simply write this. That is, what type of integers they originally are, that does not matter. We can replace them with their positive counterparts. And similar things are also there for GCD, because we already discussed this in a previous number theory video, so I am not going to say anything more on this. We just continue to use it. But k is positive, so k will come out of that absolute value sign, function. So this is equal to, now this part let me just keep it for our information. It's there, and this is why we have been able to take this step. Now we continue our calculation. K times absolute value of A and k times absolute value of B. Now this is where we use one of the previous things. In place of this LCM, you can write k times absolute value of A times k times absolute value of B divided by GCD of these numbers. What have we used here? We have used that result which tells us that if you have, say, two numbers P and Q which are both positive, okay, then the product of their GCD and LCM is equal to their product. That one we have used. So LCM will be the product of the numbers divided by their GCD. And the positivity of P and Q, here we have that because we are dealing with positive things. K is already positive, A and B being non-zero, and they give us this positive moduli. Okay, now this is K square times this divided by, now that result that I was mentioning back then, I mean whatever we are now trying to prove for LCM, we have a similar one for GCD. So by that one, this K can be taken out and you will have GCD map. Now you don't have space here. The way I have written these things, the spacing is awful, but anyway, what can I do? So K comes out and inside we are left with this. Okay, so and that becomes equal to K times, because you can cancel one K. Now you can use this result, that is this step, once more on this quotient. So the quotient itself will be LCM of absolute value of A and absolute value of B. I know it looks very bad, but let me just use this space. And again, because of these things, in place of this LCM, you can write LCM of A and B. So this gives you part B, that LCM of KA and KB is K times LCM of A and B. So that's just part B, and now let's move on to part C. In part C, it's given that M is a common multiple of A and B, and we have to prove that the LCM of A and B divides M. Okay, and we also state that we are going to follow the hint, so we start accordingly. Let T be the LCM of A and B. Then T is by definition a positive integer. Whatever it is, it ultimately is, it is a positive integer. By the division algorithm, there exist integers Q and R such that M is equal to Qt plus R. Q, that means you are dividing M by T, and you can do that because T is positive. That means T is non-zero. That's the important point. To get quotient Q and remainder R, where of course our remainder is non-negative and is less than T. Now since M and T are both common multiples of A and B, R is also a common multiple of A and B. Probably where I stand while writing these things on the board, that is not ideal, because when I write on this part, I am standing here, so you can see this part, whereas while I am writing on this part, I am standing like this, so maybe this is covered. So one of you pointed this out. Just give me some time, okay? It will take some time for me to change things and write like this. But anyway, so now what have we written here? The part where we have applied the division algorithm, that we understand, but because of this equation, R has now become a common multiple of A and B. What does it mean for M to be a common multiple of A and B? M is, because that's the hypothesis. It just simply means that both A and B divide M. Okay, and T being the least common multiple of A and B is also a common multiple. That means A and B also both divide T. So both of them are dividing M as well as T, so they will both divide M minus Qt, that means R. So that way R also becomes a common multiple of A and B. But note that we have these inequalities also. Now R is a common multiple of A and B, and R is a non-negative integer. If R is positive, then we are getting a common multiple of A and B that is less than T, the least common multiple of A and B, which of course is absurd. So that's why R cannot be positive. Since R is less than T, or okay, because we will need this one also. Since 0 is less than or equal to R, which is less than T, so R cannot be positive due to the minimal nature of T. And that's why R has to be equal to 0, which just simply forces us to conclude that T divides M, which is what we wanted to show. R cannot be positive, i.e. R is equal to 0. It is non-negative, so if it is not positive, the only possibility for it is to be 0. Thus, T t divides m. That means the LCM of a and b divides m. So here the solution ends. Next, let a, b and c be integers. No two of which can be 0. No two of which can be 0, and D is their GCD. We have seen at the end of this section, or the one before that, I don't remember exactly, the definition of the GCD of 3 integers, or in fact, if one follows the pattern of that definition, one can easily provide the general definition for the GCD of any number of integers. However, we already have the definition for 3 integers. So that's the thing we have here, and D is their GCD. Now, okay, let me just first complete writing the problem, then we will see what this condition means. Show that this I cannot risk starting here because it has 2 GCDs in one place. Okay, so this is equal to the other 3 possibilities, the other 2 possibilities, and all of them are equal to D. Okay, GCD, what is this next one? Oh, so they have taken B and C together. A and GCD of B and C, which is equal to the GCD of A and C and B, and that is equal to D. That is equal to D, which however I don't see here. It's definitely it must be the case that I forgot to write equal to D here. It should be equal to D, okay, because otherwise there is no point. Then what are we saying? If we are just simply writing this equal to this equal to this, then that has nothing to do with this. So it must be equal to D. In fact, it is equal to D. So let us now see, first of all, what this condition is saying. We are given 3 integers no two of which can be 0. That means what? That means you cannot have any two of them simultaneously 0, and because of that all of them also cannot be 0, but one of them can be 0. Okay, so that possibility is there, because you see, if one of them is 0, say A is 0 and B and C are both non-zero, then is this condition satisfied for this special case? If you take B and C, these two, of course they are both non-zero. If you take 0 and B, then they are not simultaneously 0 because B is non-zero. And if you take 0 and C, then also C is not 0. So no two of them are simultaneously 0. So this possibility is there. One of them can be 0 or all of them are non-zero. So let's now see the solution. And this condition you can of course understand. This condition has been given to make sure that these GCDs exist. We do not have any case in which say two of them can be 0. That's why it has been mentioned that two of them cannot be simultaneously 0, so that their GCD exists. So what we are going to do is that we are going to name this one something, and then we will show that that something is equal to D. And one will you will see, once you see that part, you will understand that the others can also similarly be shown to be equal to D. So we start like this. Let D1 be equal to the first one and this. Okay. Then note one thing, that this GCD, that is our D, which is given in the problem itself, this is by the definition of GCD of 3 integers. However, here we have ordinary GCD because after all, just give me a moment. After all, GCD of A and B is itself an integer, and in fact it's a positive integer, and we have C. So this is their ordinary GCD, I mean the outer one. So here we are dealing with ordinary GCD of 2 integers. Then D1 by definition of GCD, because it's a common common divisor after all. So yeah, again I should not cover that part. That's what I should keep in mind. Then this, and at the same time D divides C. Okay, but from this one, D1, but from this one we will again have the relations that D1 divides A and D1 divides B. So we are ultimately getting D1 divides A, D1 divides B, and D1 divides C. Now because D1 is dividing all 3 of them, A, B and C, so by the definition of this GCD, you go back to this definition, you will see then that D1 has to actually divide D. That means this new GCD. this implies D1 divides D. Okay. Now we have to prove the other relation, that is D divides D1. On the other hand, from the definition of D, that is the GCD of A, B and C simultaneously, D is already dividing them, the individual numbers, that we are getting directly from the definition. On the other hand, since D dividing A, D dividing B and D dividing C. Okay. Now since D divides A and D divides B, we have, by the definition of the GCD of A and B, we have this. And we know that their GCD exists because both of them are not simultaneously zero. So that condition is used here also. Similarly, since D divides this and D divides C, we have okay, in a similar manner we have this, that is D divides D1, because this is D1 according to how we are naming this. So we have got these two divisibility relations, which would give us, normally it would give us the conclusion that D is equal to plus or minus D1, but because both D and D1 are positive, so they will be equal. Since since D and D1 are both positive, we thus have D equal to D1. Okay, so we have shown that one of the three things, one of those three things is equal to D. Similarly, you can, now you understand how to show that the others are also equal to D. One can similarly show that so here the solution ends. But before we see the next exercise, let me draw your attention to one fact. What was given in our original statement of the problem, that no two integers in this list of integers are simultaneously 0. Okay, so that means GCD of A and B, GCD of B and C, GCD of A and C, they exist. But we have the outer GCDs also. How do we make sure that they also exist? That is because, you see, if you look at this GCD, the outer one, it's the greatest common divisor of two integers. One of them is C. We don't really know anything about C. C may be 0. However, the other integer is itself a GCD, so by definition it's a positive integer. That means it's non-zero, and that's why these outer GCDs will also exist. So let's now see the next one, and which is in fact the last one of this set of exercises. It will then be over. And this last one is computational. Find integers x, y and z satisfying this thing. GCD of 198, 288 and 512 is equal to that thing, 198x plus 288y plus 512z. And hint, of course, is also given. It's not necessary that you have to always follow the hint whenever a hint is given, but usually it's better to follow the hint, because the authors do not just randomly give hints. They already know what is needed, so they give a hint in such a way that it's almost always this is the case, that it's the easiest to follow the hint with whatever knowledge we may have about the object that we are studying at that stage. But if you already have some advanced knowledge, there is no need to actually follow a given hint. You can write your own solution, and it may even be easier at times. However, the hint given here is this: put D equal to the GCD of 198 and 288. Because and 500, the number 512 seems familiar. Is it a power of 2? Maybe. But anyway, that's not relevant. This is equal to GCD of D and 512. Do you see why they are equal? It is by the previous, whatever we proved just now. By that fact, this GCD is in fact equal to this. First, find integers u and v for which this GCD is a linear combination of D and 512. Okay. First, what is this thing? First, find integers u and v. For which GCD of D and 512 is equal to du plus 512v, and we will just do that. But before we can work with this, we have to actually find D, and in finding D and then the next GCD, that means the ultimate thing, we are going to use the Euclidean algorithm, of course. So we start the solution. So we first find D, and D is the GCD of 198 and 288 by the Euclidean algorithm. So let D be the GCD of 198 and 288. Okay, so now we write the equations. Note that 288 is 198 plus 90. That means you understand that 90 is the remainder here when you divide 288 by 198, and like that the other equations will now come. Then then you have to divide 198 by 90, and if you do that you get 198 is 2 times 90 plus 18, and next you divide 90 by 18, which is this. So here you get 0 remainder. That means D is 18 by the Euclidean algorithm, which we do not mention because we know D is 18. But then we are now next going to find the GCD of D and 512. So we go through another such set of equations next. 512 is, yeah, this is going to be big, but I have all the things here with me. 28 times 18 plus 8, then okay, so again we are getting 0 remainder. That means the last non-zero remainder is 2. Hence the GCD of D and 512 is 2. Okay, so this 2 is in fact the GCD of all these 3 integers by the previous exercise. We thus have GCD of 198, 288 and 512 is 2. Now we start the back calculations. We start from 2 and then follow these equations in this direction, and then this the other equations in that direction, in the backwards direction, and express. We ultimately end up having a linear combination of these given integers, where the coefficients of course are also integers, and that will that will give us what we want. Now 2 is equal to, okay, so first of all we look at the last one. Last one is this one will not be useful. This one, 18 minus 2 times 8, okay, and then the previous one, that is this one. From this one we can write an expression for 8. So this is 18 minus 2 times 8 is 512 minus 28 times 18. Okay, so it will be how much? 56. But we already have one minus and another minus, so 56 plus 118 is 57. So this is equal to 57 times 18 plus minus 2 times 512. Okay. Now next what? Next we have 18, an expression for 18 from this equation. So that next we are going to write 57 times 198 minus 2 times 90 minus, okay, it looks a little strange. Oh, because, okay, we have 3 numbers involved. So one of them can just sit like this. The others we will now have here. Okay, I hope in this space itself I will just be able to use whatever we have here, so that I don't have to lose these equations. Plus minus 2 times 512. Okay, so if we do the calculation, which of course I am not going to think mentally because I am very bad at it. So here, after we do this calculation, what do we end up with? Minus, let's just write this one first because it's just going to be like this. Plus 57 times 198, because that's just simply, oh, here we have to do only multiplication, plus minus 114 times 198. Okay, and finally no, okay, what the hell? This is not 198, this is 90. Yeah, now we can write in place of 90, 288 minus 198. Yeah. Now that we have used all the equations, we can just simply lose them. So this becomes minus 2 times 512. Yeah, it will take some time to get rid of this bad habit. Okay, so if we, how do I show this? If we multiply these two, then we will get plus 114. That we will have to add with 57. So that will be something times 198. So that means 114 plus 57. $171 times 198. And of course, along with that, we have minus 114 times 288. So the order in which the numbers are given, x is 171, y is minus 114 and z is minus 2. And one more thing is that these are symbols for the product, okay, multiplication, not decimal point. Decimal point appears here at the bottom level, whereas the dot for multiplication appears in the center, okay, in between the top and bottom level. So that's just it. If you want, you can write hence x is this, y is this, and this is x, this is y, and this is your c. That's just it. So you have been able to express the ultimate GCD of these three numbers, which is 2, as a linear combination of the numbers themselves with integer coefficients. And that just completes this solution, and it also completes this section. After this section, we have of course another section devoted to the notion of GCD, where we encounter linear Diophantine equations in two variables, that is, equations which look like this. We have two variables x and y, where a, b and c are integers, and we ask the question, does this equation have a solution where x and y are also integers? So when you try to investigate that problem, you see that somehow it is linked to GCD, and you can in fact guess why that is so. That's because if you somehow can show that C has something to do with the GCD of A and B, then you already see the link, because GCD of A and B can be expressed as a linear combination of A and B with integer coefficients x and y. That is why. So we will see all these things in the next number theory video. So I wrap things up for tonight. If you want to say something about these things, you can use the comment section below, or you can mail me. My address will be there in the description. And so today is Tuesday. This coming Friday we have the next upload, which will be on graph theory. So that's just it. So see you on Friday with graph theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.